Right, let's jump straight into this explainer. Today we're looking at the invisible, fundamental forces that hold our entire material world together. Literally every single object you interact with, the device you're watching this on, the food you're eating, even the air you're breathing right now, it is all completely dictated by microscopic interactions that we call chemical bonding.
Seriously, think about this for a second. Why isn't the universe just some chaotic, swirling soup of isolated loose atoms? Well, it's because almost every atom has this massive, microscopic problem it desperately needs to solve. And the relentless, nonstop drive to solve that problem is what actually builds the physical reality we live in.
So here's our roadmap. We're going to cover the quest for stability, electrovalent bonds, covalent bonds, coordinate bonds, and finally, comparing compound properties.
Part 1. The quest for stability. The atomic problem. Let's get right to the root of the issue.
Here is the absolute core of the problem. Most atoms are basically born unstable. They're totally restless and chemically reactive because their outermost layer, the valence shell, is incomplete. And this brilliantly explains their ultimate motivation. Atoms are constantly striving to satisfy what we call the octet rule. They just want to reach that perfect, chemically inert state of having exactly 8 electrons in their outermost shell. When you compare them, it's like two different worlds. On one hand, you've got the perfectly content noble gases, like neon and argon. They already have their 8 valence electrons, so they're totally unreactive. They're basically the VIPs of the periodic table. But everyone else, they're fundamentally unstable, constantly scrambling to copy that exact electronic configuration. They just desperately want that stability. So how do they fix it? Well, they can't just magically conjure up new electrons out of thin air, right? They have to interact with the atoms around them. This forces them down one of two primary paths, either a dramatic, complete transfer of electrons or a mutual, shared compromise. Which brings us to part 2, electrovalent bonds, the transfer. Let's see how this first strategy actually builds a bond. The mechanism here is a really elegant 3-step transaction. First up, a metallic atom generously donates its extra valence electrons, and that turns it into a positively charged ion, or a cation. Step 2, a nonmetallic atom gratefully accepts those exact same electrons to fill its own shell, becoming a negatively charged anion. And step 3, because opposites attract, those new positive and negative charges lock them together with a massive electrostatic force. You can actually see this play out perfectly with regular old table salt, sodium chloride. Sodium has this one annoying extra electron keeping it from stability, while chlorine is exactly 1 electron short of an octet. So sodium permanently hands that single electron over to chlorine. Boom, instantly. Both achieve that coveted noble gas perfection, and the resulting magnetic attraction tightly binds them into a stable compound. And you know, it's not always just a single electron making the jump. Take calcium oxide, for example. Calcium actually transfers 2 full valence electrons over to oxygen. The core principle is exactly the same, though. It's this incredibly unequal trade that magically satisfies both parties, leaving both calcium and oxygen perfectly stable as oppositely charged ions locked in an electrovalent bond. Moving on to part 3, covalent bonds, the sharing. But what happens when neither atom is willing to give up its electrons completely? Like, what if they both desperately need electrons and no one wants to lose any? That is exactly where the covalent bond comes in. It's an absolutely brilliant compromise. Instead of a one-way transfer, these non-metallic atoms overlap their outer orbits. They basically pool their resources and co-own pairs of electrons. The magic here is that both atoms get to count that shared pair toward their own outer shell, so they mutually satisfy the octet rule without actually giving anything away. Check out this hydrogen molecule. It's a super elegant solution. You've got 2 separate hydrogen atoms, each with 1 electron. They overlap their orbits, pull those single electrons together to form one shared pair, and suddenly they've created a stable, single covalent bond. It seamlessly solves the problem for both of them at the exact same time. But what if they're completely desperate for electrons? Well, the sharing gets pretty intense. Nitrogen atoms are each short by a massive 3 electrons. So what do? They overlap and share 3 pairs of electrons simultaneously. That forms an incredibly robust triple covalent bond, which essentially locks those 2 nitrogen atoms together with an absolute iron grip. Now, I should point out, sharing isn't always fair, right? When identical atoms bond, like our hydrogen or nitrogen, they pull on the shared electrons totally equally.
That creates a perfectly balanced, non-polar covalent bond. But sometimes, when the atoms are different, one pulls way harder on the shared electrons. That unequal tug-of-war pulls the negative charge closer to one side, making a polar molecule with a slight electrical charge at its ends, kind of like a tiny magnet.
And that unequal dynamic sets us up perfectly for part 4, coordinate bonds, the lone pair. Okay, to really wrap our heads around the coordinate bond, we've got to talk about the lone pair. These are basically leftover pairs of valence electrons that an already stable molecule isn't even using for bonding. They're just sitting there, fully paired up, completely unshared, and ready to go. This illustrates it so well. Take a normal water molecule. Its oxygen atom has completed its octet, but it's just sitting on these unused lone pairs. Then, along comes a hydrogen ion, which is literally just a proton with 0 electrons. The water molecule acts as this generous donor, giving a free ride to the positively charged hydrogen by providing both electrons from its lone pair to make the connection. It's a shared bond, for sure, but one atom brought literally all the supplies. Which brings us to part 5, comparing compound properties, the macro impact. Let's zoom way out from these tiny little overlapping orbits for a second. Because electrovalent bonds create these intense magnetic attractions between fully charged ions, they form really rigid, tightly packed hard crystals with super high melting points. Think about how much heat it takes to melt salt. Covalent compounds, on the other hand, are made of distinct neutral molecules. The forces between them are pretty weak, so they usually end up as soft solids, liquids, or gases at room temperature, like the oxygen we're breathing right now. And this actually explains exactly how they handle electricity. If you dissolve an electrovalent, ionic compound in water, you separate all those tightly packed ions. Once they're dissolved, those highly charged ions are completely free to move around and carry an electrical current beautifully. Solid salt won't do a thing, but salty water, it totally conducts. Meanwhile, covalent compounds mostly lack those free-moving charged particles, making them terrible conductors. So I'm going to leave you with this to chew on. Every single physical interaction you have today, the texture of the stuff you touch, the state of the liquids you're drinking, it's all just the macro result of invisible atoms tirelessly, endlessly seeking out their perfect, stable 8. But if these are just the basic natural rules of the game, what do you think happens when scientists start intentionally breaking them to engineer entirely synthetic materials? Well, that's a whole different puzzle for another day. Thanks for joining me on this explainer.